Hello friends, welcome on this video on more on modal analysis. I was enthused by the comments of one of the viewers to say something about the closely spaced modes. I found that some more topics related to the modal analysis were left out, so those things I have taken up in this new video. Up some definitions which were missed out in our previous video. So normal modes, the modes in free undamped vibration where all masses attain the maximum modal amplitude at the same time. They move in unison, then it is the normal modes. Fundamental mode, the mode associated with the lowest frequency, hence the longest time period is fundamental mode. Natural frequency is the frequency at which a structure vibrates on excitation is a natural frequency. Let us take the vibration of a system having modes 1, 2, 3 up to say mode n. Then what happens to time period and frequency? So time period is longest for the mode 1 and shortest for the mode n. So when time period is longest indicates it is moving sluggishly, slowly. Frequency will be reverse of this because they are related by a reciprocal relationship. So frequency for the first mode will be lowest and frequency for the highest mode will be highest. So this understanding is required regarding the time period and the frequency. In engineering generally we describe systems through the time periods, which is common with the engineers. We have taken a 5-story RC building and we have run the analysis. Now we want to see the mode shapes and the modal vibrations of the building. We have taken the first mode here and then we apply the animation. So it moves like this. It is moving. First mode is along the short direction of the building. Now we take this second mode, we increase the mode, this is the second mode. This moves on the longer direction of the building and the animation for the vibration in modes is like this. Third mode will be generally torsional, so we will show the third mode. Start animation. So third mode is torsional, you can see. Okay, there are many nodes in the building, so there will be a lot of modes possible. And if we take say next mode, it is like this. Some kind of corner stretching. And you can see other higher modes, say we have taken here 10th mode, say we take 10th mode and the animation under this is like this. This is the 10th mode. So this way it can move in different animations in different modes and all the modal properties are available in the analysis. For example, time period is here, frequency is in hertz is available here. This is called generalized eigenvalue problem. Now in eigenvalue, the unknown vector, say x, is appearing on both sides of the equation, and the peculiarity of the solution is this, that there is no unique solution for x. So there will be infinite solutions of x and we shall be satisfied with any one of the infinite solutions. Now in the eigenvalue problem, if we have only one matrix, say here in the equation number 2, d x equal to lambda x. So x is appearing on both sides, which is unknown, and only one matrix is there, then it is called standard eigenvalue problem. Now the dynamic equation that we discussed in the previous video can also be converted to the standard form, and the equation we have shown in equation 1 also can be converted to standard form. So what we do for that, we multiply both sides of equation 1 by B inverse matrix, then we get B inverse A x equal to lambda B inverse B x. So B inverse A matrix, let us designate by a new matrix, so it is dx, and right hand side identity matrix can be omitted, so it is lambda x. So now only one matrix and unknown vector x on both sides, so it is the standard eigenvalue problem. D equal to B inverse A. Now as I said, with our dynamic equation also we can convert it to this standard form from the generalized form. So when we write k phi equal to lambda m phi, then there are two different matrices, k matrix and the m matrix on two sides, and phi is the unknown vector. So it is a generalized eigenvalue problem. Let us pre-multiply both sides by m inverse. Now why not k inverse? Because inverting k will be difficult. It is either a full matrix or a banded matrix. Whereas m, if it is diagonal matrix, it is very easy to invert. Every element of the inverted mass matrix which is diagonal will be simply a matrix having its diagonal elements as 1 divided by the element of the original mass matrix. That is 1 by m1, 1 by m2, 1 by m3, etc. will lie along the diagonal in the inverted mass matrix. So we multiply both sides by m inverse, then we get d phi equal to lambda phi in the similar way where d equal to m inverse k. So this is the standard eigenvalue problem for the dynamic equation. This d is called dynamic matrix. Now how to solve the eigenvalue problems? There are several methods available. One method will be mentioned in our previous video. The characteristic equation method, power method, Holzer's method, Rayleigh's method, Householder's method, Jacobi's matrix rotation method, Galerkin's method, matrix deflation method, and Stodler's method, and many more. Actually, eigenvalue problem is a mathematical problem, and hundreds of solution methods are available in mathematics to solve this. However, the ones we have shown here, the methods we have shown here, are particularly useful for the structural dynamics application. The orthogonality of matrix, to some extent we discussed in our previous video. In our previous video, that is video number EQ17, we have seen the orthogonality of matrix. Orthogonality of mass matrix was shown in that video. However, there is orthogonality of stiffness matrix as well. So if we write phi r transport k phi s, r and s are two distinct separate modes, then this product will become a scalar 0, and this is your orthogonality condition. When the modes are identical, that is r equal to s, then it becomes phi r transport k phi r, which is not a scalar 0 but a scalar quantity. We write it as kr, and this is your modal stiffness for the rth mode. In the previous case, when it was the mass matrix was involved, then phi r transpose m phi r was mr, the modal mass for the rth mode. Now let us see how many modes are possible in a system. To have a feel about this, let us consider a 30-story building of plan size 25 at the rate of 5 meter and 20 at the rate of 4 meter along the short directions. So number of nodes or joints available in the system, 30-story into 25 into 20 from here, so 15,000 nodes joints are available. Since it is a 3D system, so there will be 6 degrees of freedom per node, so 15,000 to 60, 90,000 is the total number of degrees of freedom. And the number of eigenvalues and frequencies also will be 90,000. Number of eigenvectors also will be 90,000. Elements in each eigenvector will be 30 because the building was 30-story high. Now the question regarding the closely spaced modes. When the frequencies of modes are close to each other, they are said to be closely spaced. When the frequencies of modes are close to each other, they are said to be closely spaced. Closely spaced mode does not mean any healthy condition for the building. Rather, it indicates there are problems in the building structure. So firstly, there can be plane asymmetry, there can be mass irregularity, there can be torsion and unbalance, all of which are detrimental to the performance of the structure. And presence and effective appentage. Appentage means a vertical cantilever or a horizontal cantilever. A balcony is a horizontal cantilever. A tower put on the top of the roof is a vertical appendage. These appendages have their own frequencies of motion. So some of these frequencies of the appendages may match with some frequency of the main structure, or they can become very close to each other. In that case, we have the closely spaced modes occurrence. Anyway, all the four can cause the closely spaced modes. As per Indian code, closely spaced modes are those modes whose natural frequencies differ from each other by 10% or less of the lower frequency. Let us take an example for understanding. Say the lowest mode is 2 radian per second frequency. Second mode is 2.15 radian per second. Then the difference between them is 2.15 minus 2 divided by the lower mode frequency 2 is 0.075 or 7.5%. Since this is less than 10%, so as per Indian code, these two modes are closely spaced. A reference paper to closely spaced mode I am citing here. Those who are interested may go through. By Corneliu Manu, Dynamic Analysis of Structures with Closely Spaced Modes using Response Spectrum in computation structures in the given volume and pages. Now, there can be chances of resonance in a building. Resonance means the excitation frequency and the frequency, natural frequency of the structure are almost coinciding. So what is the consequence? Consequence is that the response will be very high at resonance condition. Response may be displacement, deformation, force, shear force, bending moment, whatever response quantities, they will be magnified at the resonance condition. The excitation frequency is say 1.5 Hz. Now we have so many natural frequencies associated with this structure depending on the degrees of freedom. Suppose the fifth mode has also a frequency 1.5 Hz. Since the two frequency, excitation frequency and natural frequency as fifth mode are coinciding, then there should be resonance around the fifth mode. A resonance will enhance the response higher than the normal values. We have taken a graph here to understand the resonance condition. So we have taken on the vertical axis response and on the horizontal axis a ratio, which is the ratio of the frequencies. P is the excitation frequency and omega is the natural frequency of the structure. So this ratio if we take, when P equal to omega, then eta equal to 1, and that is the resonance condition. So here gradually as we approach towards the value of eta towards unity, the response was gradually increasing and it has attained a maximum peak when eta equal to 1 or at resonance. Gradually again on the right hand side, as the eta value increases, the response decreases again. So at resonance and around the resonance, the response quantity is very high, and at that point it can cause damage to the structure. Now there is the concept of modal matrix and spectral matrix. When all the modes are put in a matrix form, we have the modes, you remember, say phi 1 is first mode, phi 2 is second mode. All these modal vectors, if we put in a sequential format in a matrix, then it is called modal matrix and given by capital phi. So capital phi equal to first mode port, then second mode port, then nth mode port in a matrix format. Element wise it will look like this: phi 1 1 element of the first row and first column, and so on up to the nth row and nth column phi nn. So this is the first mode shape vector, second mode shape vector, and nth mode shape vector vertically. So this is called the modal matrix. Now we have the eigenvalues which represent frequencies. If these are also put in a matrix form together, then it is called the spectral matrix. Spectrum means something related to frequency. It is given by the symbol capital gamma. So spectral matrix equal to first omega 1 square, first eigenvalue square, then second eigenvalue square, and so on. These are the eigenvalues, and from here, from the relationship omega equal to twice pi by t or omega equal to twice pi f, we can get the time periods or we can get the frequencies. So this is your spectral matrix. It is diagonal. Now there is a term called the modal coordinates. The real displacement vector u, actually ut, can be expressed in terms of modal vector and modal coordinates. So what is this? So u can be expressed as a summation of phi r q r, two scalar quantities, and r goes from 1 to n is the total degrees of freedom. This comes from the fundamental requirement of vectors from mathematics. And if you arrange them together, you can write it like this: capital phi, that modal matrix, and q term in the vector format. This qr is the called modal coordinate, and it is given by this expression qr for rth mode is equal to phi r transpose mu divided by mr. So this modal vector transpose, you understand, mr is the modal mass for the rth mode. So this response quantity is called the modal coordinates. It is arising out of the modal values phi and modal mass mr, etc. With the understanding in the previous slide, about the modal coordinate, the undamped free vibration equation can be expressed in a different way now. It is capital M q double dot plus capital K q equal to a null vector. What is capital M? It is the modal mass matrix we will see just now, and K is the modal stiffness matrix, and Q is the that modal coordinate we have discussed in the just previous slide. For damped free vibration, one more term will come here, the damping term. So it will be mq double dot plus cq dot plus kq equal to a null vector. So instead of the real coordinates u, now we have converted the free vibration equation undamped and damped in terms of the modal coordinates and modal values. This is some application. So M here is modal mass matrix, which is diagonal generally, and it can be obtained by taking this capital phi transpose mass matrix times capital phi, the modal matrix, and the modal stiffness matrix phi transpose k phi. Physically they will look like this. Capital M, the modal mass matrix, will be a diagonal matrix having the diagonal elements as the modal mass for the first matrix, modal mass for the second matrix, and so on up to modal mass for the nth matrix put in diagonal line, and the off diagonal elements are all 0. Similarly, with the modal stiffness matrix, K equal to modal stiffness for the first mode, modal stiffness for the second mode, and so on up to modal stiffness for the nth mode. This is also diagonal matrix. Thank you very much for watching. Please like and share the video, subscribe the channel, and you can put your queries and questions and comments on the comment box. If any queries there, I shall try my best to answer the query.